in the following experiments, we will try to hold all these things as much as constant as we can do. Sometimes with proteins or living bacteria, this is really difficult, but you'll see that we do the best we can do. So we are physicists, right? So the biologists always look at us and say, what are you doing with these bacteria on the AFM cantilever, you know? Okay, so we concentrate on these two and try to find out which one is the leading force for the different systems. And so first begin with the Wunderbar Force. Typically, if I talk to an audience, for instance, about chemists, they basically know about this one, because this is a correction to the ideal gas equation. Even the biologists appreciate, but they say, okay, but this is of short range. So I have to argue with them that in cases where we're looking at, for instance, a medium in air that covers a surface, that it is already a long range, not to talk about a sphere like a bacterium or a protein of a surface. This is really of long range. So you know all about that. And how to find out about the Wunderbar or about the relevance of the Wunderbar force, we modify the substrate. We modify the substrate that way that we care for the surface layer. So we have a layered system, and this means we have an additional component to the Wunderbar forces. So you will see we don't have the resolution to differentiate between if it's really additive and this and that. You know, take it as it is. If you can do better, please let us know. And the substrates we use is based on silicon wafers. The natural silicon if you just take a silicon wafer out of the box, it's typically covered with a natural silicon oxide layer in the range of 1.5 to 2.4 nanometers. We measure them before each of the experiment, also the root mean square roughness. They're hydrophilic, and we can also get them, buy them, or do them ourselves, oxidize them, and then get a silicon oxide layer thickness way beyond 100 nanometers. The root mean square is a little bit rougher, still the water content angle. They're absolutely identical. We did a lot of work putting into saying that the surface chemistry is absolutely identical, and it's composed of silicon dioxide. You find this out, you can look for the electronic states, you can look for the density and all that kind of things with the analytical methods of surface physics. So, both those wafers are hydrophilic, surface composition silicon dioxide. Now we can cover them with a silane self-assembled monolayer. This is a hydrocarbon chain of a certain length. 16 carbon atoms typically is the chain we're using. And then this doesn't change the roughness much, but it drastically changes the water contact angle. And this is just one monolayer of these self-assembled molecules. In other words, the surface composition now changes to its CH3 end group. Now, these two share the same surface properties, the same surface chemistry. These two share the same surface chemistry, but these two groups are completely different. Whereas these two should be nearly identical concerning the long-range Wunderbar force, because this monomolecular layer here of the silane molecules is just like a little bit thicker silicon dioxide layer. So instead of 1.5, it's then 3 nanometers. But these two also share the same long-range forces, but very different to these two, right? Because there we have this thick silicon oxide layer that shields the underlying silicon, which is much more polarizable than silicon dioxide. So with these 4 samples, we can tune now the effective interface potential. So the short-range force is governed by some type of repulsive bond repulsion. Then we add the silicon dioxide, and now we get, instead of a purely Lennard-Jones potential, because we have this second component due to our layered system, we can get these metastable potentials. In other words, with the thickness of the silicon oxide layer, we tune the long-range force, and with the silane layer, we tune the short-range force. So, if you look at liquids, the depth of this mini-movement was published, I think, 1938 by a Russian guy, in Russian by Frumkin, is a connection between the depth of this global minimum of the potential and the contact angle of the liquid on the surface. So the depth can be measured by macroscopic means. So we can fix this point for every type of liquid we have. Now, how do we get this type of potential? Well, first we now can put any type of thing on top of these 4 types of wafers. I'll show you in the following the protein, bacteria, and the gecko. But let's start with some system where we can gain many of the details as possible. So for the polymer film, it means when we prepare a polymer film, let's say with a thickness of a typical photoresist that is used for making the computer chips in your computer, well, it's about, depending on the technology, 10 nanometers, okay? So if we prepare the 10 nanometer photoresist in one of those 2 situations here, where we have a purely attractive force between the interface air-liquid and liquid-solid, if the force is attractive, this means the liquid photoresist is pushed out and it will de-wet. So this is the nightmare for Intel and all these companies. So this means that the system will slide into its equilibrium position and de-wet. On the other hand, if they prepare their photoresist on a substrate that gives them a metastable potential, then they need a nucleus to overcome this potential barrier. Therefore, they go to the clean rooms to avoid most of the possible nuclei. And in this case here, we have a special case. I don't go into detail, but it's called spinodally wetting regime, and this is the nucleation regime. And in spinodally wetting, there is a certain wavelength that is amplified the fastest, and this is imprinted on the liquid surface. And wherever the amplification is such that the valleys touch the substrate, we get a hole. And you see, they're very nicely correlated. This is a Fourier transform. And Free and Jane and Ruckenstein in the 60s published that their preferred wavelength here is connected with the second derivative of the potential. Here we are. Okay? So, what we can measure is the spinodal wavelength, this one, on the natural silicon oxide and the thick silicon dioxide. Here's the data point, the full thickness of the polystyrene film. Now, using this formula, we get a plot of the second derivative of the potential as a function of prepared polystyrene film thickness. Now, at the moment, this is just a guide to the eye, but we have to apply a model to get the data fitted. And so we thought, okay, we do continuum mechanics, we come from this side, and think of a short-range potential 1 over film thickness to the power of A, plus this summand for the Wunderbar Forces. And here's what we get. For thick silicon dioxide, we get this type of curve, and for the 2 thinner ones, we get these curves that have the potential wall. As experimental fit parameters, we get the short-range interaction constants for the 2 different oxide thicknesses. And this is, we can gain this because we can nail down this point with this error bar here in X and Y by measuring the contact angle and by measuring the residual wetting thickness film, which nails down here the thickness to 1.3 nanometers. So this point is fixed and has somehow to be met by these two forces, by the bond repulsion and by the Wunderbar force. Okay? And the rest is then also fitted. The Hamaker constants are fitted. So this experimental model system enabled us the determination of the endorsed Hamaker constants. So we didn't need to, at first place, to calculate anything. If we do the calculation, for instance, like Israel-Lachwili, using the refractive indices and the dielectric constants, we gain the Hamaker constants in the very same order of magnitude. They should actually pop up here. Okay, if you're interested, I'll show you later. Now let's go with these wafers and test the adsorption of proteins. You can think of, from your saliva, there are lots of proteins absorbing to your teeth. You could feel the biofilm if you didn't brush your teeth for a day or so. Yeah, that's what it is. A mixture of proteins and bacteria. So here's the potential, consisting of the Wunderbar interaction between protein and surface layer, and the second, the Wunderbar interaction between protein and silicon, the subsurface. Okay, for this model we assume the protein diameter of 4 nanometers, very reasonable, and here the Hammaker constants are now calculated via the dielectric properties of the involved materials, and this is what we expect from this rough model. Now we change here the thickness of the silicon dioxide, so the thick oxide is plotted here, the Wunderbar interaction in kBt, and here's the thin oxide. So think about your surface. Here's your wafer at 0, right? Here's 0, and here comes the saliva. And now there is a protein molecule in your saliva. When does it feel the attractive surface? Well, you should be below 1 kBt. So when are we below 1 kBt? Well, for the thin silicon oxide, the protein has to be as close as roughly 2 nanometers above the surface. However, for the thick silicon oxide, it has to be much closer, right? It has to actually touch the surface. In other words, if we flush a protein solution over these different types of oxides, we should get much more adsorbed proteins on the thin silicon dioxide, right? Because proteins feel the underlying silicon. Yeah, so the stronger Wunderbar forces are always on the thin, natural silicon dioxide layer. So this is just an expectation. Here we treated a protein like a single rigid molecule, which it is not, right? So it's really hard to simulate in this picture a real protein. They can undergo different conformations and stuff like that. But as a rough estimation, it should serve. And so Wunderbar forces impact indeed proteins, for instance the size. If we just look at the diameter of proteins that have been absorbed to the surface just by AFM spectroscopy, by AFM imaging, we see that on the thick silicon oxide, we see this type of diameter around 6 nanometers. Look at the lysozyme. This is a lysozyme adsorption. As a crystal, it's 3.3, 4.5 nanometers. Whereas if you go to a thin silicon oxide, we get a wider distribution, and the protein has kind of spread because it feels these strong forces from the underlying silicon. This is a long story which I cut short now. So stronger Wunderbar forces can induce morphological changes of protein conformation on surfaces. So on one type of surface, the enzyme can still be active, but on the other surface, same surface chemistry is inactive. So it's all published here. So different adsorption dynamics can be faster, can be slower, depends on the protein. We get typically more compact protein films if we face stronger Wunderbar forces, meaning we get an enhanced density. And we can also record a reduced mobility of proteins on surfaces. So they just come to the surface, stay where they are, whereas on surfaces where the attaching forces are not so strong, they're still mobile and find their preferred place. So, let's go to bacteria. This is already the microscale. Here's an AFM tip covered with a monolayer of bacteria, for instance, Staphylococcus carnosus, that lives on our skin. We can also go to the bad guys like Staph aureus, and we can also use a single bacterium and then get force distance curves like that. So here's the bacterium, one or a bunch of them. We press them on the surface, record the cantilever deflection, calculate the force, and detach it again. So this is then taken as the adhesion force. Now we have our seeded wafer and press it on and lift it off of our 4 different types of wafers. Now let's first look at the hydrophilic wafers. Here is the occurrence of a certain adhesion force for the thick silicon dioxide, and here it is for the thin silicon dioxide. And as before, on the thick silicon dioxide, we record lower adhesion forces as compared to the thin silicon dioxide. So reading publications of different groups of, well, different continents using different silicon wafers, there can be a difference of a factor of 2 just because the silicon dioxide layer hasn't been recorded. If you look at the hydrophobic surfaces, we see the same thing. So higher adhesion forces of the silicon dioxide layer, but because the silicon here adds up with these monolayer of self-assembled silane molecules, the difference is not as big as here. Still, it is there. But if you now compare the hydrophilic and the hydrophobic adhesion force, we see that staph carnosus more likes to adhere to hydrophobic surfaces. This is because the adhesion in bacteria is mediated by proteins. And obviously the proteins that are living on the cell wall of a bacterium love more the hydrophobic surfaces. So here, Wunderbar forces make up for a difference of a factor of 2, but short-range bond repulsion due to the chemical composition of the surface make up for an order of magnitude of force. Now the biologists say, okay, these bacteria on the cantilever, first, are they alive? Yes, they are alive, they can divide, we have to be fast with our measurements, otherwise we have twice the number of bacteria on the tip. And we can stain them, so they're really alive. But you put them on a cantilever, they're not mobile anymore. It's not like the mutants in your mouth. I said, what would you propose? Well, here's a microfluidic setup. Flush the bacteria in solution over your 4 types of wafers. Okay, we did that. And here's the outcome. You won't see the single bacteria yet really nicely, but I have put here a region of interest where I mark them with red dots. Now we just record the adsorption rate of the bacteria to here the hydrophilic wafer set. Dark blue is the thin silicon oxide, the thick silicon oxide, and this is the naturally thin silicon oxide. We didn't know what concentration to use, however, we always find, again, the rate on the thin silicon dioxide. So, yes! And then the biologists appreciated and we could publish the paper. Well, here, the theoretical evaluation is difficult due to the unknown dielectric properties of bacteria. It's basically a water ball in water decorated with a cell membrane. So I don't think we can do much, but having this tool, I just want to share with you that if you're using fluoride toothpaste, this is a good thing. Why? So here we have hydroxyapatite pellets mimicking very smooth tooth, and we have untreated, and we have ones that have been dipped into a typical mouthwash containing fluoride. And we now record the adhesion force, you see here in nanonewtons, for the different bacteria that live in our mouth, compared here to the one that lives in our skin. Then you see that the adhesion force is lowered by a factor of 2 again. So fluoridation causes, and this was reason number 1 that had been published for many years and had been shown in many studies, reduction of the solubility of the lactic acids that are produced by these bacteria eating up the sugar in our mouth. But another reason is that the adhesion force is reduced. So I like this story. Every time I brush my teeth with fluoridated mouth, toothpaste, I think, okay, I get rid of these nasty guys just by adding fluoride to yes, this is the same story. Now we were on the microscale, now go to the macroscale to the gecko. Gecko is the largest animal that can walk on ceilings. Let's just briefly zoom, I think most of you know the story, into his paws. They consist of long hairs that divide into smaller hairs and smaller and smaller and smaller hairs, and at the end they have a so-called spatula that makes a tiny little but flat contact to the surface. So the gecko is the master of optimizing the contact area to the surface. If we had that on our paws or on our palm, we could also stick to the ceiling. So here's the spatula from the side. It has basically the dimension of a polymer film, right? 20 nanometers in height, well, and then the width is confined. Now, we did the same thing. First, we measured a single spatula with a single zeta, and a single zeta can carry 10 to 20 nanonewton. So the gecko is about 100 grams, 70, 80 grams. So it needs 1 billion of these spatula to be able to walk on the ceiling, and it has a factor of 10 more, so he can carry a heavy backpack and still climb on the ceiling. However, the error bar was too large to see differences in the thick and the thin silicon oxide. So we said, okay, we have to be better in statistics, and used a piece of gecko skin, 0.3 millimeters, like a stem, engaged, dragged a little, mimicking the movement of the gecko paw, and retracted. We could record the lateral and the normal force. I concentrate on the normal force here. And the normal force is recorded here now as millinewton instead of nanonewton before. We can record it either as a function of humidity or of drag speed, of running speed. However, the story is always the same. We find higher adhesion forces again on the thin silicon dioxide, where the silicon is still visible. Different arrays also give the same results. Going to the hydrophobic wafer set, we first recognize that the adhesion force is still climbing up with humidity. Why this is not yet clarified. Usually, the water layers should stay constant, kind of constant on hydrophobic wafers. So from the capillary force, it should stay constant, but it does not. So we have to dwell on this further. But nevertheless, also on the hydrophobic wafer set, we record higher adhesion forces on the thin silicon dioxide. Okay. The Gecko has a big advantage that we can go into theory again. So if we have the theta close to a thick silicon oxide layer, we basically have to care about this, the surface contribution of the thick silicon dioxide in van der Waals, and compared to the thin, we need the two components. And plotting the potential, and here we took a keratin sphere, so we didn't put the real geometry of the Gecko theta. But what we see is that, again, the thick silicon dioxide potential is above the thin one. In other words, the minimum, which is a measure for the maximum adhesion force, the minimum is deeper for, again, the thin natural silicon oxide layer thickness. So it all fits into our experimental data. And I just want to share with you what, again, the formulas are. Maybe you know the Adsorption and Ninham formula. This is valid only for distances that are smaller than the thickness of the surface layer. And we developed one in 2001 that is valid for ore. It's not a big difference. It's just nice that you can use all kind of combination of X and D. And both have the surface contribution and the subsurface contribution. So this is for the Gecko, and well, whenever two objects come close and are moved against each other, there should also be friction. So how about friction? Here's again one of our wafers with a silicon oxide, variable thickness, with or without a silane SEM. And here's a silicon nitride AFM chip. It's a bit blunted, which gives better results. Now we slide this over the surface and record the torque as a friction, and vary the thickness. Here is the hydrophilic wafer set, and here's the friction force as a function of applied load. And you see that the friction force is always larger for the same applied load as compared to the thick silicon dioxide. So the van der Waals forces act like an additional applied load. Sounds pretty clear, but we had to fight for this, and yes, higher, and the same is true for the hydrophobic wafer set. The difference is a bit smaller, but for the same reason, because we have a little thicker silicon dioxide layer if we add up the self-assembled monolayer, which has about the same dielectric properties as compared to the silicon dioxide. So, again, deeper minimum for the thin layer in both cases. Now, it had been published then in Physical Review Letter after some fighting. Okay, here are the take-home messages. Long-range forces can be adjusted by a layered system. Monolayers typically change the short-range forces only. Wetting, adhesion, adsorption, and friction are a result of an interplay of forces. And if you want to predict the behavior of a certain system, you have to exactly know how your system is composed. And for systems like in biology, this is eminent important. And most of the people don't even care for what type of substrate they have. They say it's glassy, it's silicon, or whatever, it's silicon dioxide. They don't care. And the other take-home message is that adhesion is not superficial. You have the subsurface components. And a surface can reach up to 100 nanometers, which is, well, the reaching distance of the photons, right, into the subsurface. In short, macromolecules, bacteria, and geckos are sensitive like the princess on the pea. I'd like to thank a lot of co-workers and collaborators, funding agency German Science Foundation, and a very nice collaborative research center, and graduate colleges, and I'd like to thank you for your attention.
Great talk. Question?
Thank you for a nice talk. Proteins, you never mentioned other interactions that are probably comparable to Wunderbar. What do you do with that?
This is the second talk. So to check for electrostatics, we change the ion concentration, right? I have data with me. We can change the ion concentration, so the overall adsorption rate changes. But the difference is, due to Wunderbar forces, stays the same.
Another question? Sure. What about the computational part? Let's say you extract the Hamaker coefficients. Is there any way to compare that with calculations, like when you have dielectric spectra of a protein, maybe?
Do we have dielectric spectra of a protein in solution?
Some.
Really? So we have to talk to.
Can you pass the microphone?
How do you use the additive approach to calculation the Wunderbar forces for the layered structure on the sensor?
The answer is very simple, because it works.
But you know the error in comparison with the exact formula for layered structure.
So which formula would you propose?
You have to use the exact formula for layered structure. What is the error of your approach compared to the...
Yeah, so we tested that to do the full lift shits, because we also want to go to metals. But the thing is, our error bar is so large, you don't see the differences. So we can't see. So also I've already been asked, do you see retardation effects? No, right? So it's just, the width of the curve I've been showing you, this makes up for the differences. So, we don't have atomic resolution or anything. So this is not possible.
I was wondering if you have checked for different dopant concentrations of your silicon.
Oh yeah. No,
you see differences?
No, not within the typical dopant concentration which you can buy. Yeah.
Umar had a question. Do you see, for your adhesion force measurements, do you see a difference if you pull it fast versus pulling it slow? I mean, non-equilibrium.
Yes. I mean, these are large molecules. I can show you data, for instance, for proteins attached to bacterial cell wall. And if you approach, it's like you have your hair in the wind of the car. You go fast, right? So they're floppy and they're compressed or whatever. And if you go slowly, you find a snap to contact distance at distances where the thermal fluctuation extend the molecule. Very interesting data. It's another talk. Yeah.
Last question.
When you calculate the addition, like in welding, I have like a conceptual problem. How do you define contact? Like what distance you put? Because it really uses like 0.5 angstroms. I don't understand why. So.
Yeah, so this is a problem in these soft systems, right? I mean, for the friction I showed you last, it's easy because you are in contact and you press further and then you get a rigid bending of the cantilever. That's it. And for the contact, we just see that the force is, for instance, 0 or changes sign. That's all we can say. If we have, for instance, if we do force distance curve with bacteria, we first compress all the cell wall proteins together, this is one rigidity. If we press further, and we're lucky and the cantilever doesn't break, we can compress the bacterium, right? But this is 3 orders of magnitude difference in elasticity. Okay, so because of this different elasticity in the system, rigid surface of the silicon, very soft cell wall proteins, and kind of rigid bacterium, we can infer, let's say, to 0.2 nanometers the point of contact.
Okay, let's take a name again.
Yes.
Okay, okay. Okay. Now let's go to the following talk while the presentation gets. Let's see if we can see something, but now is Carsten Henkel time. So we'll be talking about forces beyond second order with electromagnetic response theory and without a PowerPoint presentation running. We see. So, Hubun Chan, let me thank you for the invitation. I see that I'm in the middle of a talk about real-world things and Kim's discussion on stress tensors. And so maybe this talk is a good transition between the two. I remember this sentence from London and Eisenschitz. Yeah, these are the 2 authors of 1930, calculation of quantum mechanics for Wunderbar Forces. And so they had the problem, we have many energy levels of atoms, all these states that fluctuate and electrons hopping around, and we don't have enough data to know all the numbers. Yeah? So their strategy was, let's try to connect the formula that we find from quantum mechanics to data that we can measure, and connect measurable quantities. And the strategy was justified by, well, we have some error bars on the forces we can measure in the Wunderbar equation of state. And of course we have error bars in the spectroscopic data we have. And so if these errors kind of match, that will work. Yeah? And so I think this spirit still continues in the field of Wunderbar forces. Yeah? So you don't have to do a very sophisticated theory, but something that is capturing the physics. Yeah? This is sometimes kind of an art. Yeah? So I will try to give in the talk more the qualitative pictures. Yeah? I realized that the Francesco's example of forces on atoms that move in front of a surface has some overlap. Yeah? But I was surprised too how I could rephrase his results in a different language. So maybe we can even understand it better. And so I would like to acknowledge his contribution. Diego is also here. Vanik Makachian from Armenia is also a very nice co-worker. And I had a former student, Gregor Piblo, who's now in Madrid, who worked on this too. So now I would like to have a picture. Yeah.
Oh, something happened.
Something happened.
Oh, no.